we will now talk about demodulating in AM signal. So, in general, an AM signal forgive my bad drawing. So, in general, an AM signal looks like this: time, and this is ST. And from this ST, want to recover empty. The modulating signal, which in this case empty is directly visible as the fine. So empty is directly visible as the M. So now, how do we do this? So we construct this circuit. So we construct this. So first of all, let's pass this through this half-wave rectifier. Fine. So this is a half-wave rectifier. All of us know this. And once we pass this signal through a half-wave rectifier, let me draw this correctly. What happens is that actually what I get is this, nothing, this, 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 this. So I hope you get the idea that once we pass this through the half-wave rectifier, we simply get the positive half, or if I use the tool available, so what I get is copy and paste over here. So if I use only the positive half cycle, or if I get only the positive half cycle, I'll basically get this. So this, and from this I want to get the envelope back. So how do I do that? The answer is simple, that let's consider RC circuit with, so let's consider an RC circuit. So let's call the signal xt for time being, and alright, believe you heard the thunderclap outside. Anyway, so next, right? Now let's say uh, considering the case where RIC is much smaller than 1 over FC, or RIC is much greater than 1 over FC, so that the capacitor charges quickly. We'll use the blue line to track the charge of the capacitor. So the capacitor charges quickly. So we see that the capacitor charges quickly to this point. Fine. Now also, so the capacitor charges quickly to this point, and now once the capacitor charges, the carrier signal decays to 0. So it will now start to discharge. So capacitor after coming to this point starts discharge, but its discharge or the time which it takes to discharge time discharge time constant discharge time constant is given by tau d. Let me call it tau d, and it is equal to tau d equals r naught c naught. Fine. So if this discharge time constant is large enough, or r naught c naught is much smaller yeah, r naught c naught is much larger than 1 over fc, then the capacitor will discharge slowly, and therefore if the capacitor discharges slowly, you will get a signal that follows this. So earlier the capacitor had to charge up fast, so this time constant should be much smaller than 1 over fc. Sorry about that. Yeah. So now if the time constant is much larger than fc, then the capacitor discharges slowly, and you get this. Now this and this. Now by the time it reaches this point, the next wave comes in, so it gets charged. Then again discharges slowly, charges, discharges slowly, charges, so on. So it can, this approximation can kind of track the envelope, but obviously you have to also take care that r naught c naught is much smaller than the bandwidth, or if r naught c naught is not smaller than the bandwidth, you'll charge to this point, but then before anything can happen, you'll stay stuck here. So you won't be able to make out much. So in order to accurately track the channel, the condition that you should have is r naught c naught less than, and this entire circuit st rit sorry ri diode. This is called an envelope. This is called an envelope detector because it detects the envelope of an AM signal, and this works only for smaller or the modulation index smaller than 1. Yeah. So this is the description of AM demodulation. We'll stop here.